Actually, if it's okay, we can start earlier. And well, this is a pretty informative session, so let us start earlier. So we have dozens of slides. Actually, it's pretty bounty, and well, I will do the first part, and Gavin will responsible for the second half. So, starting from my parts, I'd like to start, if it's okay, start from now, and I won't go into great details due to time limits. If you're interested, actually, we have a video recorded, and if you're interested, then you can follow us on Shushu Linux. Can follow our communities to it, and actually, the KSM. Well, this is not official start yet, just chatting. Well, personally, I think this is pretty useful, especially for the production developments. Well, AI and clouds are our buzzwords now, but for the foundation of this platform, it's Linux. The building bricks is still Linux, and some of the organizations still need support from Linux. And if you're using Linux, then that means you're likely to run into panic and crash. So we know that that there are panics in different ways, and so today I'm going to talk about it. I think this is the right topic for today. Well, at the beginning, I would like to spend several minutes on x64 and 86, and the mainstreams are these two structs, so I pick one of them to focus on today. So we talk about basically a mechanism or a methodology. Well, so if you develop a hang of it, then you will know their structure better. I have a lot of slides, so I'll just skip the self-intro on Benchu. So we talk about the practicing Linux crash and panic issue on production and cloud server. So for my part, I would like to introduce the KSM and cache. I would like to have a brief introduction, and we have 9 practicing examples. I will briefly go through 8 examples, and the final one, the 9th one, will be very complicated and will be responsible by Gavin. And so why do we need KSAP? Linux has been developed from for 28 years. It's pretty strong, pretty robust. And have you ever seen a black screen in Linux? Well, I think it's not frequently seen. And if we deploy it on large scale, then there's the possibility of black scale. So we're still considering the reliance of this system, and if we run the test, then you will find the possibility of crashing the whole system. So why the panic in the system? Well, so I think this is how we develop KSM page. KSM, what's KSM? And KSM is what we used when we have a panic. Then we will develop a screenshots and we save it. Later, we will restore the situation and find clues. It's like what the police do at the murder scene. We will save the crash scene, and then for later research and for maintenance and developers, especially for embedded systems and for smartphones, these developers and the personnel working on the optimization of products, they also need KSM, especially for physical devices. And when your system is not responding, we will use KSM. So it's pretty handy. And your CPU and fixed busts might cause a panic in the system. and they are not responding to reboots, so KSAM is coming into play. So what do we need to provide you with very good screenshots for research later? Well, if you're working on Linux, if you're developing Linux, including operation and management and cloud provider and totally all these relevant personnels, they will have to know KSAM better. This is a struct for KSAM. When we have a crash, we have two cores. One is called production core and the other is capturing core, and they will use KESEC to capture the cores of the crash. They will switch and develop screenshots of the memory and load it into local or network disk. And how can we provoke it? We have multiple ways. You can do it manually, and you can also do it in a system. You can set a kernel panic watchdog or shock log off and or wolf memory, etc. It will all works. And what if our system is blocked? It's a code trace that's commonly seen for 120 seconds. Well, it's probably a deadlock or other things. So if you're using KSAM, then you can better solve this problem. So you would know who have the lock, who's waiting on the lock. We will use KSAM to learn these informations. And also, if we want to develop a KSAM, then we will deploy it on server. And here, it's my recommendation is to use the x68 server. So it's pretty new and it's pretty solid, not easy to break. And also we can develop it on ARM64 platform, and ARM64 platform is commonly used now. And we have a experiment platform with 5.0 and ARM64, and this embedded platform enable you to run all the tests that you want. How can we trigger in KSAM manually? This is how to do it. After KSAM, this graphic shows you how to use the Max5 to write the memory documents, and this is using the crash tool to do the VM call. And if we're developing the DAM data, then this is pretty handy as a tool. We have a dozen of orders that you can follow. And starting from here, this is an example. Roughly, we have 9 listed here. Due to time sensitivity, I'll go through several of them. First, it's pretty simple. OOP error, and this is the whole analysis process. And this is how we analyzing code trace. For example, this is the parameter, the first one, and this is the course. This is the course for the crash in kernel, and you can read it if you're interested after the session. And this is how we run the analysis. So due to time sensitivity, I'll just skip. And this is how we check on the second parameter. Test number 2 is how we have access to a deleted list and restore the process of panic. And experiment number 3 is like experiment number 1, and this is how we visit a non-existing page, and this is a bug. And also when we're developing a driver, if we use a regu map, this is what happened. Basically, we're creating an issue, and we add one parameter in experimental 5 compared with experimental 4. And let's say the hardware is not on the want-to-be status or ideal status, then there is a deadlock. Then KSAM can capture the needed information. Experimental 6 is a bit like ARM64 computing value, and we have to analyze on the functional stacks, and it's better for you to understand the functional stacks relations. So you can read through the handbooks of ARM64. So this is the functional scheduling of ARM64, and this is how we organize the stacks, and this is the graphics. This is each stacks, and they have FP and LR, and how we store it, and this is how we finish the computing, and we have several equations. This is preconditions based on which we can calculate and compute the relations in KSAM. Due to time limits, I will just skip. This is how can we come up with the relations of functional scheduling. And experiment number 7 is like this. So how can we know each parameter, its location in each stacks? This is very important for our on-site analysis. So first, we have to understand ARM64 and their stacks, and we have to also deduct on the parameters based on recursive analysis, and we have to compute or calculate on the location of each stacks. And this is before and after the experiment. This experiment is about how can we come up with the second and the third parameters and their exact values. This is from my previous slides, and how can we get the core trace and find the code of compilation, and how can we locate the second parameters. And this is ARM64 stack layout. So only 5 minutes, so time is limited. I will skip. And experimental 8 is pretty complicated. It's remotely related with what Kevin is about to talk. And how can we use KSAM and use stacks to get the value of parameters, and then we'll know who's the holder of the deadlock. So KSAM is the key to solve the deadlock. We can basically get every information we need in the analysis process. And this is a self-developed experiment by myself, and we now get the rewrite log from MNS and PS thread. We'll also need to get the semaphore rewrite log, and if we have the two threads going on simultaneously, then there is a crash. Then how can we analyze on this example? So briefly, this is pretty lengthy, and we can see that in PSME we have 4 threads and non-traceable. We can analyze them one by one. Mainly, we will use this compilation codes to deduct on the clues that you want to find, and you will find the location of this clue in different stacks, and you analyze the logs, and you have to know the logs very well. And if you don't have a better understanding about the rewrite logging, you can read on the blue bubbles. So I will skip this part due to time limitation. And this is analyzing on the test process or threads. This is the call trace. We have a thread PIT number, and we have circled it, and this is how the test threads get the log, and we are analyzing the compiling code, and we're also using the features of ARM64. For example, ARM64 have x19 to x28 temporary change. We will have to save it for further analysis. We'll have 2 minutes, so skip it. Also, we have Kdump, who analyzed each thread one by one, see the exact location of that log, and later Gavin is going to talk about the same thing. So, sorry, due to time limit, so skip these parts and you can read it from the graphic on site. This is my self-developed threads and how it became a deadlock. Briefly, this is summarization. KSM can help us to solve the blackout, the black screen issue, and you had to know the crash tool and how to use it, and you will have to learn the basic process of analysis using crash tools, and you will have to locate the parameters by compiling code and solve problems by doing this. And then there will be no black screen for you. And now let's invite Gavin, an expert on kernel, and he will talk about a corporate level deadlock issue and how to solve it. Welcome.
Hello everyone, my name is Gavin. Yes, I would like to introduce to you that in Ubuntu Cloud Server, there's an issue we have encountered. It's very interesting but very complicated. So I won't go deep into this, like assembly, but I will talk about our concept in debugging. Yes, I hope you can learn a lot from it. So let's continue. So this case, if you want to see the detailed case description of this, but I think that yes, this is provided by Backtrace. The whole process I have recorded in it. You can click it open and view it yourself. So the problem is that of our biggest client, his machine only have over 100 CPU use, but it has like 5 GB memory, 512 GB memory. And the Nomad is enabled, and there will cause feed and hit. Yes, the Nomad D is enabled, and the few amps. There was some lockup in it. So I like to go inside and check it. So if you up it, we use the Kdump in the VM. We can see that. The lag is in the SMP core function. Yeah, if you see this line, it means that it is stuck on CPI, because TOB is unlike the ordinary, in Mancy. It uses it will be flashed. Yeah, it is stacked You can see in this line that it's stuck. But why API? If it is sent, then it gets stuck because it's waiting for another CPU. For example, I'm CPU 0 and there's another CPU 1. And they want to fresh it, the CPU. I want it to finish it so as for me to continue running, but it's stuck here. And there's no response from that CPU. This is what you can see from the film. And when you're investigating it, you can see that Linux, 4 to 5 years ago, they've been developing this for a while. They've seen there's an API loss, including people from Ingomon, and they give us some configuration, and we ask them to test it. And well, we searched for a long time, but we haven't come to a conclusion. Yes, we can't find why the API is missing. Why need to wait for it for a long time? And it's missing. So I have written a page. Yes, if I throw it and I will wait for it. If it doesn't come back, I will enter a message. If I interrupt access, I will send the API. So if I think the resend hasn't come back, then I will send it again. So the problem is not what I thought about before. When you are debugging it, you can see a lot of discussions going on. But you just trust your eyes. But it's like when you find API missing, you think you need to reflect. Am I right? Because the probability of API missing is that low, but why do I have this kind of problems? So maybe I'm wrong. I shouldn't refer to the VM. I should refer to the host, because the client won't provide us very detailed information. If you, some of the clients, the thing they told us is not true. You have to analyze yourself whether it's true or not. But the client, they depend on you for the help. So I refer to the host side. I check it log. It's Kdump. So luckily, this can be run on a testing machine. They can be verified. So this is not a production-only system. In this testing environment, we made it. When we enabled the NumID, after 2 to 3 days, it emerged. Yes, it's running very fast. When we reproduce it, you DM code to hit it. You can echo C, and it will crash. It will start the KESC. And if you enable panic and app, if you enable it, yes, it will panic itself, and you can find the VM code yourself. Yes, I'm trying to acquire the VM code. Yes, but how do I find what's in it? But what do I know it's BT? I backtrace it. There's the instruction called for each under the crash. So for each BT, if you pop it into another file, and it will fill script, and if you filter all the stacks and the remaining ones, you can see which one is idle, which one is still working. So what we want to find is that who is working, who is constantly working, and who just stays idle. because in one case you will just get a lock and you will stay idle, but the whole system is waiting for this app to appear. And so I found some code trace. This is KSMD. KSM, you can see that core procedure management. If you want to expand it, fill memory, you will just group all the similar pages together. Yeah, to merge them together. And you can open more VMs from the host. That's being done by a lot of manufacturers. This is the KSMD. It was locked. The RWMC is similar to the one Ben has mentioned. Yeah, this is the first victim is locked. Another one is huge page D. What is a huge page? Huge page. I think its page 4 will become less and less, and its TOB missing possibilities will be reduced. Yeah, you can check it yourself later. So if the huge is low, if you enable it, it turned it into OS, and they will check it will have some continuous. If you have both sides, it will merge the 4 page into 2 layers and to make it 2 PDE, because when they are screening these pages, it will get stuck on the SAM, and you cannot tell which the victim is. And the third victim is QEM. This is virtualization. When it is running, KCM arc and call and enter and into the instruction, get to the guest. But there's something happened. The VMSC, it appeared, and the 2-dimension 4. Yes, these are for the last page 4 of the VM. When we want to connect it, it gets stuck. Yes, there's KSM, huge page, and QEM. These are the 3 victims. So we want to find who's the killer, who gets the key. And this is the most important part. The client told me that when I enable NUMA D, there was something happening. And in the beginning, we won't think too much. You may think that NUMA D is nothing to do with it, but it has something to do with it. So we find the Backtrace. It's NUMA D. So what's it for? It's the auto balance of NUMA. Yes. We want to check if it's remote access. If it is, then we will move the page into the local one to make the memory latency become reduced. This is his backtrace. It found in its node. It happens to be a KSM page node. So it wants to migrate this page to SM. Yeah, NUMA D wants to make migrating pages, and it happened to find a KSM page. And but there's an issue happening during this process. Yes. When the migrating page, you want to migrate the page from this site to another one, to the business node page, but the page is with another node. So you need to have this app action. If you want to change PD, the TOB cache will be updated, need to be refreshed. To be refreshed from page table and from step by step. And we have just mentioned the conclusion. Yes. If we want to migrate this KSM page, it has over 200 YAML pages, so they cannot be copied by one single machine. Yeah, over 200 YAML pages, they are merged into one page. So I will skip the details. If you're interested in it, yeah, we have already uploaded our PDF. You can see my disassembly analysis. Because I will talk about 2 to 3 hours if I go into detail. Yes, how to get back the documents. It will be very complicated. So yeah, how to solve this problem? You need to get the thread of it. KSM has 2 trees. One is stable, one is unstable tree. So when we're merging them, so the page, if it's not stable, you cannot merge it immediately. So if you just go to ESS, so it will, page 4 will happen instantly. So we will place it first in unstable tree, and after it has been screened twice, if it's not changed, then we will place it in a stable one. So we need to look at the stable tree. We can see the same pages if they are merged into one and they are put in this stable tree. All the PTEs, they are merged into one page. The linking list has over 2 million M. And if you want to migrate page of 2.3 M, so if we need to send IPIT, and yes, there are so many complicated times. It will take a long time. I have told it. I have a list for the crash command. Follow these procedures. You can see it. So I like to KSM and NUMA balance. What is it is about? You can see this picture. If I want to process A, it was put in the CPU 0. If the process A, if we want to go to the SSS, there's a new mode SS, and the latency will become longer. And if the process A, it needs to be put in the local node. So NUMA is doing this. Yeah, if it will try its best to migrate back. If you are process E, if it's in CPU 4, but the SSU, you can see on these 2 pages, they have 2 pages. So if there are too many pages on one node, I'm not just migrating page to this node 1. I think if we want to schedule this to another CPU in node 0, so NUMA balance, it has one is to migrate node, one is to migrate process. But it's not that easy, because if you want to migrate the process, then the CPU queue, what about its loading? Will the loading be affected? Is it enough? So that's not the key point. I want to keep it clear. When the NUMA is enabled, there's a NUMA balance. And the page happens to be the KSM page. When the pages merged together, they are over 200 MB. So need to do the TOB fresh, and it causes the performance issue. And if about this performance issue, like the Brandon Greg, they have done the CPU graph. Yes, when IPU is refreshed, you can see the new ID. You can see the migrate pages, and yes, these are the key points. You can see the bar is too long. When the work, what is work? The map. Yes, it's reverse MVP. The ones whose PTE is, and you do the IP ID, and this one is AF is here. The total AF is here. So how can we do it? Yeah, we want to shorten it. The upstream does not have a code. In 2015, the engineer Pinkley, he proposed it, but was rejected by the Hill Kings. So he wants to shorten the time. And if you can see our discussions, we sent this FlameGraph to him, and after a few months, the page was KSM and the merge list was shortened. Yeah, the whole process, the whole story is about it's like this. And because Ben Shushu asked me here, he knows. Yes, you can refer to this because nothing can be obtained from online telling you how to do it in detail. Yeah, that's the end of my presentation.
Any questions? The time is already up. 2:30, so 2:10, so time is limited. So if you have any questions, you're more than welcome to communicate privately.